Welcome back to the class on power semi-connected drives. In this lecture, we are going to discuss about the speed control methods of a three-phase induction motor. The speed control methods of a three-phase induction motor is classified into the two types. One is stator side speed control. Second one is the rotor side speed control. Suppose if we control the parameters in the stator side to change the speed of a motor, that is nothing but a stator side speed control methods of a three-phase induction motor. Suppose if we change the parameters at a rotor side to control the speed of induction motor, then it is called as a rotor side speed control methods of a three-phase induction motor. When you come to the stator side speed control, stator voltage control, stator frequency control, pole changing method, V by F control. When you come to the rotor side speed control methods, rotor resistor speed control method, slip recovery power control method, all six methods we can apply for the slip ring induction motor. But if we come to the squirrel cage induction motor, we can apply the four methods only because we don't have any control rotor side of a squirrel cage induction. So now we are going to see one by one each method. Stator voltage speed control. In this method, we apply the reduced voltage to the stator winding of a three-phase induction motor. The torque developed in a three-phase induction motor that is equal to 3 by omega ms v square rr dash by s divided by rs plus rr dash by s whole square plus xs plus xr dash whole square. Already we know this formula. For a high value of the slip, all these parameters are constant except this voltage. So the torque is directly proportional to the V. As the applied voltage to the stator of induction motor decreases, the torque developed in induction motor also will be decreases. Once it is decreases, the speed of the motor will be decreases. This is the slip torque characteristics of a induction motor. These characteristics are nothing but at a rated voltage. These characteristics are nothing but a reduced voltage. Constant load torque. If you find the slip means reduced voltage slip is more, nothing but the speed of induction motor will be lesser and compared to the rated voltage what we apply to the induction motor. So the developed torque is decreases. The slip of the induction motor will be increases for given load torque. Once it is increases, the speed of the motor will be decreases. But in this method, the more losses will be occurs in a rotor of a induction motor. So the efficiency of induction motor will be decreases. Generally, this method is suitable where the speed of the motor decreases with a developed torque. We can use this method for the fans and pumps. For the domestic purpose only, we can use this method. Moreover, the rating of the motor also should be the less. Now we're going to see the second method. In case of pole changing method, there are two methods are there. In the first method, in this method, two windings are placed in the stator winding, which are wounded for the different number of poles. This is the stator winding, this is one winding, this is another winding. Suppose if we take the four number of poles, this is wounded for the six number of poles. Depending upon the speed of the motor is required, the excitation is given to the particular winding. Suppose we want to run the motor at a high speed. Already we know the formula for the synchronous speed. NS equal to 120 F plus P. This winding is designed for the four poles. So synchronous speed will be higher. So the speed of the motor also will be higher. So the upper winding is designed for the high number of poles. Nothing but synchronous speed will be decreases. So the speed of the motor also will be. So depending upon the requirement only, it give the excitation to the stator winding. It is very simple and also costly because the stator winding should consisting a two winding. Moreover, this type of construction should be given by the manufacturer itself. These are the slip torque characteristics of a two different poles. This is for 6 pole because the synchronous speed is more. This is for the 12 pole. The synchronous speed will be lesser, so the speed of the motor also will be decreases when compared to the 6 pole induction motor. In second method, we assume that the six number of coils are presented, that is divided into the two groups. This is coil 1, this is coil 2, this is coil 3, this is coil 4, this is coil 5, this is coil 6. The first group is nothing but a 1, 3, 5. The first group is consisting of 3 coils and second group is consisting of 3 more coils, that is the 2, 4, 6. Now we are sending a current such a way that how the poles will be created within the winding. If the current is entering into the first group, the same manner, in second group, the current is leaving. If you apply the right hand thumb rule, the north pole will be created here. Here the south pole will be created for this direction of the current. The same manner, here this current is passing in this manner. If you apply the right hand thumb rule for all these coils, the north pole will be created. But in this coil, second group, we are sending a current in this manner. Reverse direction we are sending in this manner. Again, if you apply the right hand thumb rule, you find the how the flux is creating. 2, 4, 6 coils are creating a south pole. Total how many poles it is creating means for this direction of current is 6 poles. These coils may connect in series or parallel, but we should not change the direction of the current through the grouped coil. Suppose if we change the direction of current through the grouped coil means the number of poles also will be changed. These are the two different connections. This is series connection. This is the group 1. This is group 2. A, B, C, D. These two groups of the coils are connected in series. The second case, again, this is one group coil. This is another group coil. These two groups are connected in parallel. Make sure that the direction of the current should not be changed. But here in group 1, the current is entering into the A terminal. Here also the current is entering into the A terminal, leaving from the B terminal. But when you come to the second group, the current is entering into the D terminal. See here, the current is entering into the D terminal, leaving from the C terminal. So without changing the direction of the current in the grouped coil, we can connect these grouped coils in a two different manners. One is the series connection, another one is the parallel connection. Now we are going to change the direction of the current through the second grouped coil. In second group coil, the current is entering into the B terminal, leaving from the C terminal. Now, the current is entering into the C terminal and leaving from the D terminal. By the time 12 poles will be created. That we are going to see here. In case of C, now the current is entering. There is no change in the group 1. So here no north pole. But here again, if you apply the right hand thumb rule for all these coils, within the coil, in this area, the north pole is created. That means 6 north poles are created. So obviously, in interpole region, south pole has to create. That 12 poles will be created if you change the direction of the current for the second group coil. In first case, only 6 poles are created. In second case, the 12 poles is created. Only we have changed the direction of current for the second group. Again, we can connect these two group coils in series as well as a parallel without disturbing the direction of the current through the group coil. That we have shown here and here. Already we have seen the slip torque characteristics previously for the 6 pole and 12 poles. For the 12 poles, the synchronous speed will be decreased, so the speed of the motor also will be decreased. For a 6 pole, the synchronous speed will be more when compared to the 12 pole, so the speed of the motor also will be more. But in this case, we change the direction of the current through the group coils only. We increase the number of poles in a stator winding. But it is a complex. We have a one circuitry to change the direction of current through the coil, but it is a cheap when compared to the previous. Now we are going to see the variable frequency control. In this method, we are applying the variable frequency of the voltage to the induction motor so that the synchronous speed of a motor will be changes. Already we know that the synchronous speed of a motor equal to ns equal to 120 f f equal to frequency supply, p is the number of poles. As the frequency changes, the synchronous speed also will be changes. But here one disadvantage is that we know that the EMF induced in induction motor E equal to 4.44 kd Pp f by Pp. This is not there. Nothing but a number of poles per phase. Kd is nothing but a distribution factor, Kp is nothing but a pitch factor, F is nothing but a frequency of the supply, phi is nothing but a flux. So we know that once the design of the induction motor is over, all these parameters are constant except frequency and phi, because we are going to control the frequency. So take the frequency this side. If we neglect the voltage drop in a stator winding, the applied voltage is equal to the EMF induced in a stator winding. So V equal to U. So V by F proportional to the flux from this equation. Suppose the frequency increases, constant voltage, the flux will be decreases. The frequency increases, the synchronous speed will be increases, the speed of the motor will be increases. One side of the coin. Another side of the coin is the frequency increases, the flux will be decreases, the maximum torque developed in the motor will be. So one more important parameter here is that suppose we want to decrease the speed of a motor. So we have to decrease the frequency. So the synchronous speed will be decreases. Once it is decreases, the speed of the motor also will be. If the frequency decreases from this equation, the flux will be increasing. If the flux is increases, the machine will be saturated. More number of core losses will be occurs in a induction motor. The efficiency of the induction motor will be. These are the different speed torque characteristics of a induction motor with a variable frequency. This is a higher frequency. This is a rated frequency. This is the frequency less than the rated value. The frequency decreases, so the maximum torque developed by induction motor also will be. If the frequency increases, the flux will be decreases. The maximum torque developed by induction motor also will be decreases. That we can observe in the slip torque characteristics of a induction motor. So for given induction motor, it is not prescribed to change only the frequency for getting the variable speed. The next method is the rotor resistance speed control. This method we can apply only for the stepping induction motor. We can't apply for the squirrel cage induction motor because it does not have the provision of adding a resistance to the rotor circuit. Resistance in the rotor circuit is increased. The speed torque characteristics is shown here. In the previous method, as the frequency increases and decreases, the maximum torque developed in induction motor will be affected. But in this method, the maximum torque developed in induction motor is not affected. But slip at which the maximum torque occurs. In first case, here the maximum torque is occurs. Second case, this is the maximum torque is occurs. Slip corresponding. Third case, slip corresponding to the maximum torque. The slip at which the maximum torque occurs in induction motor will be affected if we add the external resistance into the rotor circuit. This is the increasing order of the rotor resistance. For given load torque, if you see the slip, this is the low value of slip. This is the high value of slip when compared to this one. This is the high value of the slip when compared to the second and first one. As the rotor resistance is increases, for a given load torque, the slip of the induction motor will be increases. Nothing but the speed of the induction motor will be decreases. The main disadvantage of this method is the losses is more due to the additional resistance added to the rotor circuit, and efficiency of the motor will be decreased. This method can be applied for the slip ring induction motor only. Next, slip power recovery control. In this method, we are injecting some amount of voltage to the rotor circuit. This method also we can apply only for the slip ring induction motor. We can't apply for the squirrel cage induction. By some external means, we are injecting some amount of voltage to the rotor circuit. This is the equivalent circuit of induction motor. This is stator winding, this is rotor winding. In the rotor winding, we are injecting some voltage through the slip ring. This voltage can observe or injecting the power into the rotor circuit. If this voltage is observing a power, then the net mechanical power available will be decreases, so the speed of the motor will be decreases. Suppose if this voltage source is giving a power to the rotor circuit, the net mechanical power developed in a motor will be increases, the speed of the motor will be. In this method, you can control the speed of induction motor by means of a slip power recovery control. These are the different methods are required when you're going to study the power semiconductor drives course. So we have briefed about the different speed control methods of induction motor. Thank you very much. If you have any doubt, you can ask me directly or you can ask in the comment box of my YouTube channel so that I am always available to answer all your